Hey there, have you ever really stopped to wonder what's going on under the hood of your computer? When you type a message or click on something, it feels kind of like magic, but it's really all about turning simple data into information you can actually use. So today, let's pull back the curtain and find out how your computer really thinks.
So let's start with the big mystery, right? How does this box of metal and plastic actually understand a sentence? I mean, it can't read English, it can't read any human language at all. The secret, it turns out, is that it speaks a completely different language.
All right, let's jump right into the first part of our journey. See, before a computer can do anything, it has to translate our world into a language it can understand. And believe it or not, that language is incredibly simple. It's built on just two numbers.
Here's the key difference. We humans, we use the decimal system. We've got 10 digits, 0 through 9. Computers, though, they use something called the binary system. It's a language of pure simplicity that's built on just two digits, a 0 and a 1. That's it. You can just think of it as off and on, or false and true.
And each one of those zeros or ones, it's called a bit. The absolute best way to picture a bit is as a single light switch. It can be off, that's a 0, or it can be on, that's a 1. This is the absolute smallest, most fundamental piece of information a computer can possibly work with.
Okay, so one light switch by itself isn't all that useful, right? But what happens if you line up 8 of them in a row? Well, that group of 8 bits is called a byte. And with 8 switches, you suddenly have enough different on and off combinations to represent every single letter, number, and symbol on your keyboard. But how do all the different computers in the world agree that one specific pattern of ones and zeros means, say, the letter A? Well, that's where text codes come in. They're like a universal rulebook that everyone agrees on. An early one was ASCII, mostly for English, but today the big one is Unicode, which is powerful enough to let computers represent characters from basically every language on the planet. So, now that we understand the language, let's go meet the components that actually speak it. We're heading into the very core of the machine now, the parts that do all the real thinking and remembering. This is where the magic really happens.
At the very heart of it all, you'll find the CPU, which stands for Central Processing Unit. If you think of your computer as a person, the CPU is, without a doubt, its brain. This is where all the calculations get done, all the instructions get followed. Basically, it's where all the decisions are made.
And this brain really has two main parts that work together. First, you've got the control unit. It's like a traffic cop, directing the flow of information and telling all the other parts of the computer what to do and when to do it. Then you have the arithmetic logic unit, or ALU. This is the math genius, the super fast calculator that handles all the addition, subtraction, and logical comparisons. Now, a brain is no good without memory, right? The first type is RAM, or random access memory. A great way to think about RAM is as the computer's temporary workbench. It holds all the apps and files you have open right now. But it's called volatile memory for a reason. This design makes it incredibly fast, which is great. The trade-off, though, is that the moment you turn the power off, poof, the workbench gets wiped completely clean. So to contrast that, you've got ROM, or read-only memory. This is the computer's permanent, long-term storage. So if RAM is the fast but forgetful workbench, ROM is the slow and steady memory that never forgets. Its main job is to hold the critical startup instructions, you might have heard of the BIOS, that tell the computer how to wake up in the first place. You actually use this kind of non-volatile memory all the time. Flash memory, which is what you find in USB drives and camera cards, is a perfect example. It's how all your photos and files get stored safely, even when they're not plugged in to any power source.
Okay, so we've got the language, we've got the brain, and we've got the memory. But how does all of this happen in what feels like the blink of an eye? Let's take a look at the components that are all about giving a computer its incredible speed. Every single computer has an internal clock, and it really does act like its heartbeat. It's a tiny little piece of quartz crystal that vibrates at an incredibly precise frequency. Every single tick of that crystal sets the pace, synchronizing all of the CPU's operations. And the speed of this heartbeat is just staggering. We measure it in hertz. 1 hertz means 1 cycle or 1 tick per second. But the computer you're using right now, it operates at several gigahertz. Giga means billion. So we're talking about billions of cycles every single second. It's an almost unimaginable speed. But, processing billions of cycles a second is totally useless if you can't move information around just as quickly. And that's where the bus comes in. Think of the bus as the information superhighway system inside your computer.
It's the network of electronic pathways connecting all the critical parts.
And there are two main types of these highways. You've got the system bus. That's the main interstate, the really high-speed connection between the brain, the CPU, and its temporary workbench, the RAM. Then you have the expansion bus. These are more like the local roads, connecting all your external devices, like your printer or your mouse, to the rest of the system.
Now, to make things even faster, computers use a really clever trick called cache memory. Imagine a small, private express lane built right next to the CPU on that information highway. The cache holds the data that the CPU uses most often, so the CPU doesn't have to waste time going all the way out to the main RAM to get it.
And to be even more efficient, computers usually have multiple levels of cache. L1 is the smallest and fastest, and it holds data that was just used. L2 is a little bigger and tries to predict what the CPU might need next. Sometimes there's even an L3, which is bigger still. It's this whole clever system designed to anticipate the CPU's every need.
And this is really the key takeaway. A computer speed isn't just about one single component. It's about this incredible teamwork, this perfect harmony between the fast processor, the clock setting the pace, the wide bus moving data, and that clever cache anticipating every move. They all have to work together perfectly to make your computer feel instant.
So think about it. We've gone on a journey from a single on-off switch all the way up to a system that performs billions of operations every second. We've decoded the language, we've met the brain, and we've toured the information highways. Now that you've got this foundation, the only question left is, what part of the digital world are you going to explore next?